I have here a graduated cylinder. There are markings on the side, but I've also got a meter stick here. Now what I'm going to do is I'm going to, there's a hole. There's actually a little tube coming out the side of the cylinder, and I'm going to fill the cylinder with water. Now you can see the level of the water in the cylinder, and now I'm going to release the my finger over the tube, and you see that we get a pretty good stream of water. Now I'm going to catch that water because I don't want to get it all over the floor. A little bit won't hurt, but let's get it all set up so that you can actually see everything's going on. And I'm going to catch the water in the bottle. Okay, so what you see is the depth of the water is continually decreasing. So we're going to keep this up until the water stops flowing. We'll see how long that takes. And of course you can okay, now water's still flowing. We can see it's still dripping. But there it seems to have stopped. Okay, at some point the water stopped flowing out of the cylinder. So here are data taken from the video, the first part of the video that you just saw. All I did was I played that portion of the video and I estimated the y-coordinates from the ruler at various times. And I stopped the video at 7 different times, wrote down the clock time in minutes and seconds, and the depth as best I could read it. And I think these are probably good to within plus or minus, probably within plus or minus 1, at most plus or minus 2/10 of a centimeter. Okay, plus or minus 2 millimeters. Now, changing the clock time, measuring the time from the first instant, which is at 1:01. So letting the 1:01 instant be 0, I let the time be 0 at that instant. And the 24.5 centimeter depth, of course, corresponds to that time. Then the 1:04 time, well, that's 3 seconds after the 1:01 time. So if the 1:01 times are 0 time, then that's going to be 3 seconds. 1:09 is 8 seconds after 1:01, and so forth. 1:31 is 30 seconds after 1:01. So I've done my clock times relative to the initial timing, the initial instant. And of course the depths are the same as they are here. Now if I sketch that graph, I get a graph that looks something like this. It's not a linear graph. The water isn't descending at a constant rate, as you know from having done the experiment. And I can sketch a curve, and actually the curve I sketch turns out to go pretty close to through all the points the way I've sketched them here. And if you sketch these points accurately, it turns out that the curve, it can be drawn very close to going through all of the points, but a couple of points are either a little high or a little low. Now, what we do next is very similar to what we did with the linear model. I pick 3 points on this curve. Okay, so I sketch my curve, I pick 3 points, 1, 2, 3. And I estimate the t-coordinates, and I estimate the y-coordinates of these 3 points. And I'm going to use these 3 points as a basis for getting a model for this curve. Now my estimates for these t-coordinates are 6, 17, 15, 8, 26, 3. Just based on the trend of the numbers here, and those are fairly reasonable estimates. And it turns out, and we'll see what the procedure is for doing this, but it turns out that the model for this data and the model that fits the data extremely well is a quadratic model instead of a linear model. That's why we can't do a linear model. It's obvious that there's a curvature here. Quadratic functions give us parabolic graphs that have curvature, and they have a kind of a nice curvature for certain applications. So we have this curvature that needs 3 points to accommodate. If I get 3 good points on this graph, 3 representative points, I get a good quadratic model. And the model that corresponds to these 3 points, well, I'm going to write that down here and then just talk briefly about how it's obtained, and then we're going to go to some different data and actually work through obtaining the model. The model corresponding to these 3 points is this quadratic function, y equals 0.0273 t squared minus 1.573 t plus 25.46. A quadratic function is a function that has a t squared term, a t term, and a constant term. A linear function would just have the t term and the constant term, and the coefficient of the t term would be the slope of the graph, and this would be your y-intercept. Now, this is the y-intercept, but we don't have just one slope. We have changing slopes, and this excuse me, t squared term is what causes the slopes to change. Okay, now we could evaluate this model just like we did linear models. We could plug t equals 0 into this model, and we would get, well, we get 0 for this term and 0 for this term, because each term is multiplied by at least 1 t, and t is 0. And so we just get 25.46. Well, our observation was that y was 24.5. So there's a discrepancy between what this model predicts for t equals 0 and what we observed for t equals 0. And that discrepancy is about 1. It's actually 1 point, or actually it's a little less than 1. It's 0.96, but it's very close to 1. So the y value we observed and the y value predicted by the model differ by about 1. So there's a deviation of about 1. Now we could calculate deviations for the rest of these points. We would get a 0 deviation. No, never mind. Pretend I didn't say that. Okay, we don't get a 0 deviation because we didn't use any data points. We used points that lie on the curve that we sketched rather than data points. So we're going to move on and use some different data and see how we can actually obtain one of these models. Okay, this is the model that fits these 3 points. There's a better model that takes into account all 7 points. That model is going to be called the best fit model. This is an approximation to the best fit model.